Exponential functions. So exponential functions, f of x equals some base. We're going to call that base a. That's just a number. And then we've got a variable in the exponent. And so the most basic form of that exponential is written like this. There are definitely some transformations that we can do that manipulate it, shift it up, down, left, and right, that sort of thing. All of those rules are still the same. So like if you wanted to extend that form, that this plus k, that's going to be like the plus k was on any other function we've done. It's going to shift it up or down. And then the x minus h, that's going to shift it left or right if something is happening in there. And then if there were a negative in front of the whole thing, it's going to reflect it across the x-axis. We're going to rely on a lot of graphing with our calculator with this stuff. It's going to help us to see what's happening with the function, because when things are exponential, they get large quickly, really quickly. Or they get small really quickly, depending on what your base is that you're dealing with. So the graphing calculator can help us a lot with looking at the domain and the range of these things, and actually finding function value too. So I'm going to show you some of those things with the calculator as well during this section. So let's just start with a function and talk about some characteristics of that function. So here's our first one. F of x is equal to 4 to the x power. So we've got a base of a 4, and x is our exponent. And our domain, we're going to talk about that, and we're going to talk about the range of this graph. So the domain for an exponential function is going to be from negative infinity to positive infinity. 99% of them, that's the correct domain. Okay, very few does that change things out of that. The range, remember, range deals with the y value. So a lot of times to talk about range, the best thing to do is graph the function and then look at the graph, and it'll help you find that range. So let's do that with this one. We're going to graph 4 to the x. So I'm going to hit y equals. I've cleared out any of the other stuff that I had. So just go down to whatever equation you had something in and clear it. And then I'm typing in 4 and then the caret symbol to get the exponent and put the x there in the exponent. So 4 caret symbol, which is a little housetop looking symbol, and then x as the exponent. And then I'm hitting graph to look at what's going on there. So we see this graph. It's really flat right here, coming from left to right if we read it left to right. And then when it gets here close to the y-axis, it shoots straight up. That's the exponential nature of things. When, like I said earlier, exponential things grow fast. Okay, when we think about exponential things, you think about like bacterial growth. You think about, why does the flu go around so fast in the wintertime? Well, it's exponential growth of those germs. That two, one of them splits apart becomes 2, and then those 2 splits apart becomes 4. 4 splits apart becomes 8. It just keeps growing faster and faster as that goes. So that's what we're dealing with exponential. So it's going to grow really fast. So when we look at this graph, we can see that it hugs the x-axis and then it goes up as you read it left to right. So the range for this is going to be from 0 to positive infinity because it's going up. And we're going to put a parentheses on the 0 there. If we were asked to find some function values for this particular function, let's say we were asked to find f of 1, that just means put a 1 as the exponent. And a couple of different ways to do that with the calculator. One way is to just type in 4 raised to the first power. We know that answer is 4. Or if you've got the graph or the equation in your y equals menu, you can actually hit trace and then type in the x value you want to plug in. So if we plugged in a 1, hit enter, it gives me back that y value that I'm looking for. So if they ask me to find f of, 3, that's really 4 to the third power. I know I can actually type that in my calculator and work it out. I know what 4 to the third power is. Or I can hit trace and hit a 3. hit enter, and it gives me back that 64. 4 times 4 times 4 is 64 anyway. So so I get a y value there based on a function value. Also, we could plug in a negative number. Let's do a -2. Would be a good one. This goes back to those exponent rules that we talked about last week. That's really 1 over 4 squared, and we know that that's 1 over 16. Your calculator kind of loses its power there a little bit because it thinks it's not smart enough to when you're graphing it. If you hit trace and then type in -2, it's going to give you back a decimal for that, and you can't make it change that into a fraction in this particular view. Okay, so that's an issue that just know that, hey, I could do it just the old-fashioned way, 1 or 4 raised to the -2, and then it gives me that decimal, and I hit math, enter, and it'll change it to a fraction if the answer choices are all in fraction form. If they're in fraction form and you want to change them all to decimals, you could do that too as a way of doing that. We know that that's 0625 out of that. So finding function value, being able to just type it straight in the calculator or use that trace function on your calculator is always helpful as well. And it gets you actual values that go with that. Let's look at another one that's got a different base. Let's say we had g of x is equal to 1/2 raised to the x power. So that base for this one is what I call a small fraction. You can have fractions that are are improper fractions that, like 3 over 2 is an improper fraction. Well, this one, technically is called a proper fraction, but I like to call them small fractions because they're less than 1. Okay. If you look at the graph of that fraction or that equation, I'm going to clear out that parentheses 1 over 2. And then raise that to the x power. If we look at the graph of this one, it's going to be a lot different than the one that had 4 as the base. When you got a fraction, a small fraction as the base, the graph kind of turns around. It looks a lot like the first one we had, but it goes the other direction. So if we read it left to right, it's coming from positive infinity and going down toward the x-axis there as you read it left to right. So the domain is still the same, though. It's still from negative infinity to positive infinity because it still moves left to right for all numbers. The range, if you read it bottom to top, is still from 0 to infinity. The difference is that this first one is what we would call exponential growth. Example A is exponential growth because it goes up and to the right. This one would be called exponential decay because it goes down and to the right. So when you look at that graph, it's getting smaller as you move to the right. It looks like it flattens out, but it's actually just getting smaller and smaller until the fact that you can't see the space between it and 0, the blue line and 0. So this is exponential decay. So if we find some function value out of that, so if let's say I did g of -2, that'd be 1/2 to the -2 power. If I went to my calculator and hit trace and -2, I get a +4 as my function value. If I did g of 0, that's 1/2 to the 0 power. I know the rule is anytime it's to the 0 power, the answer is 1. But if I went to my calculator and I hit trace and then 0, I'd see that it crosses the y-axis at 1 there. So anytime you need the y-intercept, just type a 0 in for x, and it's going to tell you where it's crossing the y-axis at. And then if I go a little further to the right and pick a g of maybe, let's do g of 3. It'd be 1/2 to the 3rd power. When I look at that number, it trace 3, I get 0.125. which I know is actually 1 over 8 out of that. As I move to the right further, if I did g of 6, it would be 1 over 2 to the 6th power, so it's a smaller fraction. So as I move to the right, it's decaying because the y values are getting smaller and smaller. That's why you call it exponential decay. So the difference in growth and decay is the base. Growth will have a bigger base, as in something bigger than 1. Decay will have a base that's smaller than 1. That's how you can tell the difference in the growth and decay. Growth has a base bigger than 1. Decay has a base smaller than 1. And then that's just classifying something as growth or decay. It's not a big deal because you can always look at the graph and kind of see what's going on if you need a specific answer. But if it's more of a general question of, is this exponential growth, decay, or is it exponential at all? If it doesn't have that kind of shape to it, it's not exponential. If it's moving up and to the right, it's growth. If it's down and to the right, like this one is, down and to the right, then that's decay. So the graph really can tell you everything you need to know, but just recognizing that from the equation can really speed you up sometimes out of that. Let's look at what does putting the negative in front of the base do. So like we had f of x is equal to negative 3 to the x. So that is not a negative 3 as the base. It's a negative and then a 3 to the x power is the way that works. So when you put that in your calculator, you can just type it exactly like it's written there. And the calculator is going to read that like it's 3 to the x power with a negative in front of it. And when you graph that, it has that same shape. So it's exponential because it has that shape. But this one goes down. You know, instead of going up and to the right or up and to the left, it's going down and to the right. That one technically is not exponential. Technically, it is exponential decay because it's getting less and less as x grows, but it's a reflection across the x-axis is what's going on there. So this has a domain from negative infinity to positive infinity, just like the other one. The range flips over on this one, though, because the highest value is 0, and the lowest value, this continues on down to negative infinity here if we keep going. So, 0 to negative infinity is the range for that one. Or actually, I wrote that backwards. It should be negative infinity to 0 because you read bottom to top. Sorry about that. And same thing goes, though, if you wanted to find a function value, you just plug the x number in for x and work it out. And you could do this exact same thing that we've been doing there. So we're going to rely on that calculator to graph it for us a lot with this. It is the easiest way. If you wanted to work it out, you just make sure that you don't put parentheses in there. Like if you worked out that's negative 9. And if you did f of 2, that's what I'm doing there. So that's negative, and there's 3 squared happens separate, so that's negative 9. That's how that's happening. Big difference in that problem, and if the function was this, negative 3 to the x. Those are not the same. If that's the case, some different things happen. So let's look at the graph of that. Parentheses, negative 3 raised to the x. Get the graph of that. It doesn't show up there because it's moved it quite a bit of ways away. All right, let's see, zoom fit. Right, 0. There's a little blue speck up there. This is way zoomed out. Okay, they're not going to do this to you. They're not going to put those negatives inside the parentheses there. It's kind of just a completely different situation happening when you have a negative base out of that. When we're dealing with exponential functions, we're going to deal with a base and then manipulate that from there. Let's look at what other transformations can happen out of that. F of x is equal to 3 to the x plus 2. So the plus 2 is inside of the exponent there. That's what's going on there. And let's talk about the domain and the range of that. So again, be able to type that into your calculator and graph it, because that's going to tell you pretty much everything you need to know. So I'm going to put 3 and then the caret symbol, which is right underneath clear, so right there. And then I'm going to put x plus 2. And we'll hit graph. Let me hit zoom 6 so I can get back to normal. Zoom 6 will always set you back to the 10 by 10 window. And that one looks a lot like example A did, but it is shifted to the left 2 units because you had this plus 2 inside with the x. Remember, that's a horizontal shift. So it shifts it to the left 2 units. But as far as domain and range goes, it doesn't do anything to it. As far it's still from 0 to infinity for range, negative infinity to positive infinity for the domain out of that. If you had f of x equals, and we'll use the same base, 3 to the x, and then the minus 2 on the outside of that, that transformation is a shift down 2 units. So if you shift down 2 units, you're going to affect the range, but you're not going to affect the domain. Okay, the range, since I'm shifting down 2 units, my range is going to be from negative 2 to infinity. I can see that on the graph if I graph this problem. If I go to my y equals menu and I hit 3 raised to the x, and then a minus 2 on the outside of that, I'm going to see it shifting it down, and we can see, where's it get flat at? It gets flat at negative 2. We can see that on our graph there, what's going on. If you're ever in doubt, just pick some of these x values that are out here and plug them in, like negative 3. That's almost negative 2. If I hit negative 4, I get even closer to negative 2. If I hit negative 5, I get even closer to negative 2. If I hit negative 6, I get even closer to negative 2. What if I hit negative 20? Oh, that's not on my page. Let me do one. Negative 10 will be on my page, so I'm going to hit that. Negative 10. That's a good one. Whoops. Trace. Graph. Trace. Negative 10. There we go. And that right there, that is almost negative 2 right there. Negative 1.999983. That's the same as negative 2, right? So we can see it flattens out right there. So you can kind of see what's happening. We could see where it's crossing the y-axis there. Trace 0. And there's your y-intercept out of that. So you can find those things out of that. So we see those transformations coming back that we talked about way back in Math 100 and all that stuff. So the graphs are really going to tell the tale on the exponential function ideas. Domain and range are the bigger picture things that we're looking at, and looking to see if we can solve, find the y-intercept of that. See where it's crossing the y-axis at, which is where x is 0 out of that. Okay. In this same section, we start talking about solving exponential equations using certain strategies, and then we get into actually applying them to some money type problems. Okay, so let's look at solving some equations, and then we'll start applying this into some money situations with this. So same section, we'll call this example F, and it's just solve. And I want to show you how we can go about solving these particular equations. We're going to talk about later on some other ways to solve, but this way is using exponentials to solve. So the idea here to solve these is to get the base the same on each side. So key is to look at the side the exponent, the variable is on, and look at the base on that side and to say, okay, can I break 5 down in any way? 5 is a prime number, right? It's 5 times 1. It doesn't break down in any way. So I know that if I'm going to get the bases the same, that this 125 must be something with 5 as the base. So what I want to do, and it goes back, I like to go back to what we've done before, that factor tree idea. Remember doing those things? And since I know the base I want is a 5, I'm going to divide 125 by 5. So, I would just 125 divided by 5. It's 25. So I got a 25 here. 5 doesn't break down, but 25 does. It's 5 and 5. So what we end up with here is being able to rewrite this problem. The left side is still 5 to the x. The right side is still 125, but we're rewriting it in a way that's clever, that has a 5 as a base. There's 1, 2, 3 5s. So that's 5 to the third power. All right. And now, since the bases are the same, then that means the exponents must be equal to each other. So x must equal 3. And we've solved that equation using exponentials. We're going to learn some other ways to solve equations tonight too, but this is using exponentials to solve it, which for a lot of problems, it really makes it the easy way to solve. Okay. Let's look at another one. Same idea. Let's say we had 3 to the x equals 27. So a little smaller number, a little easier to deal with. 3 I know is a prime number, so I know I can't break that down. So I look at 27 and say, okay, 27, how is that related to 3? It's 3 times 9. And then 9 is 3 times 3. So this ends up being 3 to the third power. And on the left side, we got 3 to the x. Because the bases are the same, the exponents have to be equal to each other. So that means x equals 3 again for this problem. Maybe we had a problem, an equation that had 2 to the 3x power is equal to, let's do 64. A little bigger number. Well, I look at the side that has the variable in the exponent, and I look at the base and say, can I break that base down? Well, 2 is a prime number. It's 2 times 1. There's no way I can break that down further. So that means I'm going to break down the 64 using 2s to try to figure that out. So I'm going to break down 64. 2 goes into 64 32 times, and 2 goes into 32 16 times. 2 goes into 16 8 times. 2 goes into 8 4 times, and 4 breaks down into 2 times 2. So there's 1, 2, 3, 4, 5, 6 2s that are there. Okay, so that means that my equation can be written like this: 2 to the 3x equals 2 to the 6th. Now, because the bases are the same, the exponents have to be equal to each other. Okay, because they've already told us this is equal. So that means the equation we've got to work is 3x equals 6. Set the exponents up as the equation. That's what we're making there. And then we just solve that equation, and that's a pretty easy one to solve. Divide by 3. X is... And if I went back and plugged that into my original problem, it'd be 2 raised to the 3 times 2 power, which is 2 to the 6th. And we already know that, hey, 2 to the 6th is 64. We worked it out to find that. So we're trying to change the base so that they're the same. Let's say we had 4 to the 5x equals maybe 32. A little different problem. The bases are the 4 is not prime, right? and I think about 32, 4 goes into 32, but it's not going to go into it, a nice way, in that way that we could write 32 as 4 to a power. But 4 could break down into 2 times 2, right? So this is where those exponent rules are going to come back into play that we talked about last week. So we got 2 squared, and then that's to the 5x power. And on the right side, the 32, I know that that's 2 times 16, and then that's 2 times 8, and that's 2 times 4, and that's 2 times 2. So that's 1, 2, 3, 4, 5 2s, 2 to the 5th. And then I set up my equation, and I got to do a little bit of exponent rule work, because the 4 turned into 2 squared, and that was all raised to the 5x. What's the rule that I have to do with those 2 exponents there, the 2 and the 5x? That ends up being 2 to the 2 times 5x, which is 10x. Okay? Because the rule for exponents is if you multiply, it's a power of a power is what that's called. So that's going to be, set up my equation then to be 10x equals 5, and then I divide by 10 to solve, and reduce that to 1/2. All right, so there's an instance where we had to change both sides and get the bases the same. We didn't change its value, we just changed the way it's looking to try to get it to work out for us. Let's say we had maybe a little tougher equation. 3 to the x plus 1 equals 9 to the x. Well, the bases aren't the same, so I can't set up an equation to solve yet. So I got to get the bases the same. I know 3 is prime. 9 is not. 9 is related to 3. It's 3 times 3, right? So that's really 3 squared to the x. This is 3 to the x plus 1. Goes back to that exponent rule again. Here we got, multiply those two together. So that's 3 to the 2x over here, and this is 3 to the x plus 1. Now the bases are the same again. That's what I want to happen. If the bases are the same, that allows me to set up this equation. X plus 1 equals 2x. So I'm just taking the exponents. Once I get the bases the same, I drop them and look at the exponents and set those equal to each other and solve it. This is a little tougher equation. It's not too bad. It's still, subtract x to get the x's together, get like terms together. 2x minus 1x is 1x. And then divide by 1. X is equal to 1 on that one. All right. Not too bad. It just takes a little practice. So we had 4 to the x plus 5 equals 8 to the x minus 1. All right. So we're going to take these and try to get the bases the same. So 4 and 8, they're related, but not exponentially. 4 times 2 is 8, but that's not 4 to a power. So when we see a problem that has variables in the exponents, we want to think exponentially related. But I know 4 is actually 2 times 2, and maybe 8 is 4 times 2, and then that's 2 times 2. So that allows me to change those to a base of a 2. So 2 squared to the x plus 5. And this one would be 2 to the third to the x minus 1. And then we got to follow those exponent rules that says, okay, take those and multiply them together. 2 times x, 2 times 5. will be 2x plus 10. Same rule over here on the right. We're going to take that 3 and multiply it to both of those pieces. That'd be 3x minus 3. Notice I've dropped the base of a 2 up here because they're the same. Once I get the bases the same, that allows me to do that. Okay. And then I'm taking that equation and just solving it. Get x by itself. So I get like terms together. So I'm going to subtract 2x, and then I'm going to add 3. It's going to be 13 is equal to x, or 1x, and I divide it by 1. Get that same thing back. And again, because it's an equation, that allows me to just plug it back into the original and check it to make sure it's right. The good news is I don't have a whole lot of issues with these because the exponentials, the domains from negative infinity to positive infinity, so there's nothing that x can't be to worry about. Let's do one more. Try to make one up here that's got a little bit more going on to it. Say we had 2 to the x squared plus 3x equals 8 to the 4x. This one throwing a little bit more involved equation that's going to be in there, but still not going to be too bad, I think. And just going to take us a little bit of, we see an x squared in there, we know it's going to be a little bit tougher to do. You think factoring or quadratic formula. So again, first step though, because it's exponential, we got x's in as exponents. We got to think get the bases the same. If possible, we're going to get the bases the same. So 2, it won't break down any, but 8 we know is 4 times 2, and that's 2 times 2, so it's 2 to the 3rd power to the 4x, and then this is 2 to the x squared plus 3x. And then I take that exponent rule there, 3 times 4x would be 12x. And the left side, there's no exponent rule to deal with, so we get this problem. X squared plus 3x is equal to 12x. Because it has an x squared in it, what do I need to get the problem equal to? 0. Subtract 12x. There's my 0 on one side. We got x squared, and 3 minus 12 would be negative 9. So x squared minus 9x is equal to 0. And then I've got options as far as solving that goes. I can take that and solve it by quadratic formula or factoring. I think factoring is the easiest way here because you can just do a GCF of x and then get x equals 0, x minus 9 equals 0, and add 9. X equals 9 and x equals 0. Those are the two answers for that problem. If you go back and plug those in up top, 0 plus 0 is 0, 2 to the 0, and 8 to the 0 are the same. It's 1. If I plug in a 9, 9 squared is 81 plus 3 times 9, or I could do this, 2 raised to the parentheses 9 squared plus 2 times 9, 3 times 9. Get that answer, and then take 8 raised to the 4 times 9. It's exact same huge number. Exponential, it's not unheard of to get answers that big, or problems that work out to be that large a number. What that stands for, calculator language here, this capital E like that is like scientific notation. If you remember scientific notation, it's like 3.25 times 10 to the 32nd power. That's what that stands for. It has all this other decimal jazz going on out of that, but that E stands for times 10 to the whatever powers after that. That's how it does scientific notation out of that. Not that that shouldn't affect anything you're doing as far as solving the equations, but when you go back and check, you might end up getting something weird like that. All right, so solving those equations, they won't do too many like that last example there. Like, they're not going to get too crazy on how hard those problems are going to be. Maybe later on we'll get to the other stuff tonight. They get a little tougher, but not, again, it's not going to be too many of them that are that bad out of that. Okay. So if it's from section 4.2, you got to get the bases the same. Okay, get the bases the same on those solving equations. All right, so also with these exponential functions, let's talk about compound interest. Compound interest has a formula, A equals P parentheses 1 plus R over N to the NT power. All right. A is account worth. P is your principal investment. We'll talk about these as we go along. R is your interest rate. N is the number of times compounded in a year. And then T is time in years. This formula is the formula that's commonly used for like savings accounts, how they figure up your interest that you earn in a savings account or a cash deposit, a CD, or any kind of interest-bearing account. The compound interest formula is generally used for that. There are some special accounts that do some different things, but most basic accounts use this. All right. The principal amount or the principal investment, that's how much money you put in the account. You put it there and you leave it there. The interest rate, make sure that we convert that into a decimal as we work these problems. So if it says it's a 5% interest rate, you're going to change that to 0.05 for 5%. So make sure you change that to a decimal. The number of times compounded in a year, that's if it says quarterly, which is common for savings accounts to do it quarterly. Well, how many quarters are there in a year? There's 4 of them. That's what makes it called a quarter. 4 quarters in a dollar. Quarterly is 4 times. Semi-annually, 2 times. So N would be 2. If it's annually, N is 1. If it's monthly, N is 12. If it's weekly, it's 52. That idea with that. So bi-monthly would be 6 times a year. So they're going to use a word there. Not going to come out and say, here's the number of times it compounds in a year. They're going to say those words. So we just got to kind of figure that part out. And then the time, it's always in years. So if they say 6 months, then you need to convert that into years. It's 0.5 of a year. Okay, so time, when you put that number in, it always should be done in the terms of a year out of that. So what we're going to do is we're going to take a couple of scenarios and figure out what the account is worth after a certain amount of time if we invest a certain amount of money. And then we're going to take that idea and solve for how much money we need to put in the bank in order to have a certain value after a certain amount of time. So like planning type investment out of that. So let's start with just plugging in and working it out type problem. So letter on M, I think. Example M is we invest $2,500 into an account earning 6% interest. If you find one of those accounts, please email me and let me know. I haven't found any that earn near that. It earns 6% interest compounded quarterly. For, let's say we put it in there and we're going to leave it for 2 years. The account worth at the end. So that's what I'm trying to do, is figure out what this account is worth that earns 6% interest compounded quarterly for 2 years. So that all of this information is the stuff that I need for my equation. P parentheses 1 plus R over N to the NT. So P, the principal, that's the $2,500. That's what we're putting in the bank, and we're going to leave it there. We're not going to transfer it back out of savings into checking like I'm bad to do, because I'll get nervous and say, I better cover that. Transfer it in and out. The interest, 6%, that's going to be our rate R. And remember, we got to convert that into a decimal. So we want to move it twice. So that's 0.06. So when you put that in there, you know, convert it into a decimal. So move it to the left twice. And that gets you a 0.06. The quarterly, the word quarterly tells us that N is equal to 4. So that's how many times you're going to get that interest, put it back into your account during a year. And then the 2 is your time. So that's time in years. We're just plugging those in and we're just going to work it out. We're going to use the calculator to help us work it. Hopefully ends up being a decent amount of money. I don't know. 2 years, not long to leave it there. So I've never been blessed enough to have 2,500 laying around. I hope you have, but I know I haven't. So I'm plugging in the P 2,500 here, 1 plus the rate 0.06 divided by 4, the number of times it's compounded. And then the exponent on those parentheses is going to be the N4 times the time, which is 2 years. So it's 4 times 2 as the exponent out of that. I'm actually not going to work any of that out by hand. I'm just going to let the calculator do all that work for me. So I'm going to type in 2,500 parentheses 1 plus 0.06 divided by 4, close the parentheses, raised to the 4 times 2. And I might actually just normally typed in an 8 there because I know that number. So, and then hit enter. And that tells you how much the account is worth after 2 years. $2,816.23. That was right. Yeah, 23 cents. That leftover change after the 23 cents, the bank keeps. And believe it or not, that adds up if you got enough accounts. And they get a lot of extra money out of that. So they round to the nearest cent. And if you owe them money, they round up to the next cent to make sure that they get their money back. Fun. Financial institutions. Hey, I don't blame them. If I loaned money, I'd want it back too. They get a little bit more than their share sometimes. All right, so just plugging in and working it out, finding out what's going on there. Let's look at that same idea, except for we don't know how much our principal investment should be. Let's say we know we need a certain amount of money after a certain amount of time. So we know, hey, in 5 years, I want to be able to buy myself a car and pay cash for it. And maybe some idea like that. We in my high school we teach the Dave Ramsey personal finance class that they give us the curriculum, and we use it just because it's good and informational, and it's really some sound advice. I don't know. I don't do the envelope thing, but I know people that do, and they do well with it. I enjoy living it up a little too much. So let's look at how much should we invest to have. Let's say we're going to buy a pretty decent car, $15,000 car. After let's say 10 years. We don't need it. We needed something sooner than that. Let's do 5 years. In an account earning, let's say we found a good like a cash deposit or some sort of mutual fund, and it earned 8% interest monthly. And again, if you guys find one of these accounts that actually does that, email me. Let me know where you found it and who do I need to call to move my money there. Interest rates are pretty low right now. 8% would be phenomenal. All right, so we don't know how much we're going to have to put in the bank here, but we're hoping that we've got some money set aside that we can just put in this account and let it ride for 5 years. That's the idea with this. It really complicates things if you start saying, okay, I'm gonna put $100 in right now, and then in a month I'm gonna put 200 more in there and all that stuff. So it really you would have to figure up your interest for different for the balance at each point out of that. And the good news is the banks can do that with a nice computer program that does all that stuff for them. So what we're doing is we're setting up this problem with the things that we know. So there's our formula again. We do not know the principal investment. That's what we're looking for. We know the account worth after 5 years and the interest rate, and that it's monthly. So N equals 12. Okay. So N's going to be 12. Time's going to be 5. The interest rate's 0.08. And the account worth's $15,000. That's the parts we know. So we're going to set up this equation. 15,000 equals principal times 1 plus rate 08. 12 times a year. 12 times 5 for the exponent. Okay. So the variable is right here in the front. So what's going on between this variable and all of this stuff over here is that it's multiplying to it. So if I can just work out that number, 1, let's do parentheses, 1 plus 0.08 divided by 12, close the parentheses, raised to the 12 times 5. That there. I'm not going to round it. I'm going to use the calculator's storage because it's got several more decimal digits after that. But, you know, on my paper, I'm going to write 1.48 ... times P. Okay, so there's this number came from that parenthesis. Okay, and all the math that I've got to do is just divide by that 1.48 junk into 15,000. So to do that with your calculator, you're going to hit 15,000 divided by, and here's how you get your calculator to recall that answer that you've already got in there, so you don't have to type all those digits in. And you know, maybe if you just swap two of them like that, it makes it a completely different problem. So to get it to use this answer up here, you hit second and then the negative sign, and then it'll do this ANS. That stands for answer. So it'll use the last answer it got. The last answer it got was this decimal stuff here. Okay, so I'm dividing 15,000 by that. $10,068.16. I need to round it up. so that I make sure that I've got 15,000 at least in there. So that's how much I need to invest. My principal investment would be $10,068.16. Yeah, that's right. That's how much I would have to invest in order to, at the end of 5 years, have 15 grand laying there to use. And normally, if you have a higher interest bearing account, you got to leave that money there anyway. If you take it out early, there's a penalty anyway. So, like a CD, there are different levels of them. Some of them are 6 months, some are a year, some are 2 years. You can get them to 7 years. Where the money is locked in there for that amount of time, and you get a higher rate if you lock it longer. It just means you don't have access to it. And if you got to take it out, you lose some money out of that. So that's how you can get a higher interest rate out of that. So there's using compound interest out of that. So that's compounding interest a certain number of times a year. There's another type of interest that most banks don't use, but it is possible to use. It's called continuous interest. Continuous interest has a different formula. It's a much easier formula to remember, in my opinion. It's account worth is principal times e to the RT. I call it the PERT formula. Okay, that e is the exponential number. It's about 2.71 and some change, and we'll talk about that more as we go through this evening. That is not a variable e. That's the exponential number. It's about 2.71 and then a bunch of decimals after that. And I'll show you where we can get that with our calculator. Same idea. But the P is still the principal investment. The R is still our rate. And that's still our time. All that stuff is the same. Continuous interest means that it's all the time. Where this formula comes from is if you increase the compound interest formula, if you take n and start increasing it to a larger number over and over and over, just continually getting bigger and bigger, as that number of times that you compound interest gets closer to infinity, it approaches what this formula would actually get. It levels out to that spot on that. It's kind of where the exponential graph flattens out there. So it'll say the word continuous interest in the problem. You will see the words compound interest or continuous interest, and that tells you which formula to use. And on the final, you'll have access to your notes and everything, so you'll have these formulas there for you as well. And I'll probably have them on your answer document, like I did. The answer document for 100 had a lot of formulas on it. This will be on the 110 one. If not, I'll make sure I post it for you to bring it. Let's look at a problem with continuous interest and see what we can do with that. Letter round O. Let's do a continuous interest problem. So we invest. Let's say we did play a scratch off and we got $1,000 on that. That'd be nice. And we just put that in our savings account. And let's say I have a 1.5% interest savings account. Interest compounded, and here's the word continuously. What is the account worth after let's say 4 years? Let's say I did that and left it there for 4 years to see what happens to it. Okay, so 1.5% compounded continuously. So that PE to the RT, hurt. The principal investment is 1,000. E to the rate. Again, we're going to set that as a decimal, so it's 0.015. And then the time is in years, so 4 years. And we're just going to work this out, find out what the account is worth. The account, so you're going to take 1,000 times E to get the E with your calculator. So this is the important part. I'm going to use this quite a bit this evening. Second, and then the LN button gets you the E. Second, LN. So we're going to type 1,000 times second LN over here just beside the 4. And then we're just going to put in that information, 0.015 times 4 years. And this will tell us how much our account is worth that draws 1.5% interest compounded continuously for 4 years. We didn't make much money. $61.84. $1,061.84. 1.5% interest, not very much. That doesn't counteract inflation. Inflation rates around 3%. So over the course of a decade is what inflation rate is. So you'd be tough to justify leaving that money there. We'll just go buy some more scratch-offs with it. That's what I would do. Be fun. All right. So same idea. If you were asked to find the principal investment you needed, it's going to be a division problem out of that to solve. Let's do one of those. So how much should we invest at, let's say we had a 2.5% continuous interest to have an account worth say $6,000 in 15 years. So 15 years is our time. Our principal investment, we don't know, but our account worth, we do know. So when we're setting up that problem, it's a continuous interest, so we know it's the PERT formula. So we're going to plug in the things we know. We know 6,000 is what the account should be worth. We don't know the principal, but we know E to the 0.025 times 15. Out of that. Again, we're just going to divide 6,000 by this number, whatever that number turns out to be. Second natural log to get the E, 0.025 times 15. There's that number, 1.454991415, and then it's got some decimals after that. Okay, so I'm going to take 6,000 divided by second negative sign and use that answer. It's using more than the digits you see. Hit enter. So I need to have $4,123.74 and put that in this account. If I do that, I'll have $6,000 at the end of 15 years. That's if I just put that amount of money in there and don't put any else any other money in there. Okay, so that's what the simplicity of what we're doing is. We're just doing one investment. We're not continually putting money in there later to get that. So exponential functions and some applications of those here. I'll go ahead and write 4-2. There's several problems that you could do 1 through 99 in that section. In your textbook could be useful for doing that. Let's see. The next section is really got a lot of examples. Let's take a short break and then we'll come in fresh on the next one. It's kind of changing gears and going into logarithms. So let's take a break real quick and then we'll come back and we'll get into logarithms and we'll deal with logarithms for a couple of sections and then we'll get into some equations again to finish up with for this evening. Okay, so let's take a short break with what we're doing. Be back in here at 5:20. That's about a 10-minute, or well, 5:25. That's a good round even, nice good number there. 5:25. We'll get started.